Hi everyone. This video is hopefully going to be part of a series where I try to build a 27 Mhz radio controller receiver. Those that have seen some of my other videos will have seen I managed to make a 27 Mhz transmitter before, but the receiver's always been a lot more difficult. So today I'm going to be working on a step in that process, and we're going to base the receiver design based on this design here that I found on the talkingelectronics.com website. And we're not going to do the whole receiver today, we're just going to work on one part of it. And the part that we're going to work on is going to be the part called the amplifying stages, and that will be a section of this circuit. One thing to understand, this circuit diagram here, this part here is really joined on there, so it's meant to be this long picture of the whole thing. And this Q4 here is that Q4 there. And there's a little bit of a confusing thing, because where that overlap is, we see this 22 nanofarad capacitor on this version of the drawing, but we don't really see it on this second half here, so we're going to work out whether that's even meant to be there. But in terms of today, we're going to build the amplifier portion, so that's pretty much none of the bottom here. It's going to be the section from here in and through these three transistors, and that's what we're going to cover. Right, in case you're all tempted to skip to the end to see if it even works, this is the circuit when it was fully built, and we've got the 5-volt power supply driving it, and we've got a signal being generated by my signal generator, which is very, very small. I'm showing this at 50 millivolts per division for the yellow line there, and then we've got a 1 volt per division for the blue line, which is the output. So we can see that we've got something going on and lots of amplification. So now we're going to pull it apart and work out it one bit at a time and figure out what everything's doing. So the first thing we're going to do is we're going to just build the network that's leading up to the input of the amplifier. So the real output node on this circuit that's going into drive is here, this point here, but they've got some extra stuff going on with this 4K7 resistor going up to effectively the power line, and it's 22 nanofarad capacitor going up to the power line, as well as the path through this 1K5 resistor, then this 22 nanofarad capacitor into the first transistor. Now he talks about why that is in some of the notes in here, but basically he's siphoning off the 27 megahertz out, I think, effectively, so that we're only getting a low frequency signal through here of between 600 and 1200 hertz. So I'm going to build that structure anyway, and then I'm going to put my signal generator as the source at this point here. So it's still going to look like this. We'll have our 4K7 resistor and our 22 nanofarad cap, both going up to what is sort of the power line. I'll talk about a little bit exactly why it's not quite that. Yeah, and then at this point here, this is going to be the signal gen coming in into here. And that, when I said it was not quite the power line, you'll see that if we follow that path there, there's this 220 ohm resistor that then flows out and onto here to this 78 LO5, so it's a 5 volt voltage regulator, so we're going to have 5 volts on that power rail, but there's this 220 ohm resistor in the path as well. So on my side of things here, we've got our power supply, which is this, and power coming in here onto this rail on the breadboard. Then this particular resistor here is bringing that 5 volts into this line here, and then after the 220 ohm, I've got a red wire running and another red wire running, and then that's on the power rail of this breadboard. So everything on the power rail of this breadboard is after that 220 ohm resistor. So then we have our 4K7 and our 22 nanofarad cap. So that's this here going up to the power rail, and the cap also going up to the power rail. I'm just going to draw that. I've drawn that here with a 5-volt supply, the 220, and then here is our supply going in there. And then the other part of the circuit we're actually getting the feed in is through this 1K5 resistor and then a 22 nanofarad cap going to the base of this transistor. So that's effectively out of this point here. We're going to draw ourselves a 1.5 kilo ohm resistor, and then our 22 nanofarad cap. Now I didn't actually happen to have a 1.5k resistor, so I've combined 3 resistors in series to get about 1.5k, and then here's my 22 nanofarad cap. And then in general the signal line is going to be this yellow the whole way through the circuit, but basically this point here is this point here in the process. Okay, so then we have our transistor, and they are feeding that transistor with a 4K7 from this power line. So we have a 4.7k resistor here, and that's going to come into the collector of the transmitter, and they have a 470, so quite a high value resistor coming up here and coming into that same point where it joins onto the collector, like so. This is our 22 nanofarad cap over here, and you'll see they also have a cap here, but I'm going to leave that out to start with so we can see what that's, sorry, they have a cap here, so I'm going to leave that out to start with so we can see what's going on. And let's just finish this off. So this out of the emitter of the first transistor, that goes down to ground, and the output point from this transistor is going to be out through this 22 nanofarad capacitor here. So that's coming off the collector side of this transistor. So what we're seeing is signal in here and signal out here, and this is grounded or not attached to the in and out. So we've got ourselves a common emitter configuration of an amplifier there, and instead of the normal for me biasing where you'd have a voltage divider biasing this transistor, they've done it another way with the 470k here feeding off this line here. But he basically says in the notes in the sheet work there that he's trying to get about half the 5-volt rail here of 2.5 volts or something like that, so you've got your maximum swing range. But I thought it'd be interesting now if we put a signal on here and check what's going on in here, like what behavior do we get? Do we get amplification, etc.? And then we can sort of figure out from there why maybe he's added that other cap and things like that. So what I'm going to do now is this transistor here represents that, and here's the 4.7k resistor coming off the power line effectively, and then this one here is emitter base collector, so it's jumping from collector to base. That so it's this resistor here, and we have got the source signal coming in here. So I'm going to remove that other cap because we haven't put that in our diagram yet, and I'm also going to remove this other cap, which was then the feed onto the next transistor, so that's not there either. And I'm going to pull out the other 2 transistors as well, just so that the rest of this sort of side of the circuit is not really involved. Yes, there's some power coming in, but other than that, it's sort of, with no transistor there, it's really got kind of nowhere to go. And we've removed this joining capacitor here, so there's not really anything going on this side here. We're just dealing with the first transistor here. So let's hook that up. So here's my signal generator, and out of that I have on the end of the signal generator yellow for my signal line, and it's pumping in here, and that's going to be this point on our chart. And what I'm going to do is I'm going to put out a signal there, and then I'm going to take my oscilloscope probe here, and that yellow line of the oscilloscope is going to be on the same point where the signal generator is feeding in. And at the moment we can see that we have on the scope we've got a 10 kilohertz sine wave coming out of the signal generator and through that initial network. And then I'm going to take my other scope probe, which is blue here, and I'm going to put that effectively on the output point of this first common emitter amplifier and see what is going on. So I'm going to place that here, which is on the collector, and I'm going to give these wires a bit of a jiggle because, yeah, there we go. Okay, so we can see our yellow sine wave coming in, and it's only got a fairly low voltage swing in it, so you've got 50 millivolts for division for yellow there. But you can see on the blue line, so the output of that transistor on the collector, we've got pretty much rail-to-rail swings going on. So what we're going to do is change have a bit of a go with playing with the frequencies and stuff and just see what the behavior is. But also I'm going to drop the amplitude of the initial ingoing signal so we can see how much amplification we've got going on. Okay. So we can see now that a input signal of only like maybe 60 to 70 millivolts peak to peak, which is this yellow signal here with a bit of noise on it, is resulting in a output signal of 3 volts peak to peak on the output. So quite a lot of gain there, because and then if we what we also might do is we're going to just play around with the frequencies here and see if the signal drops off or anything like that. So I'm going to start, first of all we'll get back to, yeah, okay, so then go to the frequency, and I'm going to start pushing up the frequency on this thing to, okay, now we're nearly at 200 kilohertz, and we can see that we have had a bit of a drop because the peak-to-peak voltage is now 1.8 volts, although the peak-to-peak on the inputs also seems to have dropped a bit. So maybe that's been caused by some of the signal leaking back out through this cap here. But the range that we actually want to be amplifying, based on what they've said, is only the 600 hertz to 1200 hertz. So let's sort of push things back that way. So I'm going to start bringing down the okay, so now if we adjust this a bit, that's 2000 hertz, and then we bring it down a little bit further. Okay, so this is the 1200 hertz of what we're actually wanting to amplify. So it seems like it has a fairly flat profile in terms of as you change the frequency, we're not having a huge drop off in around the range of what we're talking about. We can see we've got like quite a lot of noisiness on the actual signal that's also getting amplified. That's why they've got this sort of thick blue rather than a nice clean line. And let's see what happens now when we go and take that extra cap and we put it in across here, as they have suggested here with this. Where are we? 2N2. So 22.2 nanofarad between the collector and the base. Okay, so I'm going to take a little cap. We're going to put it in between the collector and the base. Oh, and look at that. So a couple of things that happen. That blue line is a lot more clean looking. Let me just take it back out and put it in again so you can see the difference. So that's before, and this is after. So it doesn't seem like it has as much noise on it. Those higher frequencies have been sort of cancelled out or lost, filtered, I guess you could say. And the other thing is the amplitude now has dropped hugely. So without the cap in it there, we were talking about like 2.8 volts peak to peak, and then when we put the cap in, we are now only like half a volt, like 500 millivolts peak to peak, and our signal, so that's that blue is what I'm talking about there, this measurement here, but the signal is a 60 millivolts peak to peak coming in, and if I take it back out, hasn't really had any impact on the input signal at all, but definitely reduced the gain a lot and taken away a lot of the noise. Let me now draw that cap on my diagram. So this is the cap that we're adding in here, and it was a 2.2 nanofarad cap. Did a few more measurements both with and without that cap in, and I sort of varied the range from about 1 kilohertz up to 30 kilohertz. And what I've done here is I've just plotted on graph paper the difference between having the cap in and not. So I've got a range here of 0 to 30 kilohertz. I took some measurements of the input signal, and it was at 70 millivolts peak to peak the whole time going in. And then without the cap, the output sort of ranged between 2.8 volts peak to peak and 3.3 volts peak to peak across the frequency range. And you can see that sort of plotted with this pencil line here, where around 1 to 2 to 3 kilohertz we're actually improving our gain a bit, but then it's a very, very flat profile of the gain up to 30 kilohertz. And then I've drawn in the yellow line once we had put in this 2.2 nanofarad capacitor, and you can see the huge difference between the gains. It's a lot less with the yellow one, but you can also sort of see that this drops off fairly quickly as the frequencies sort of go up above 3 kilohertz. And I re-plotted that same data with a 0 to 500 millivolt axis range there, so you could see it more pronounced. So here we can see after about sort of 3 kilohertz we really are dropping off our gain across the range up to 30 kilohertz. And at the 1000 sort of kilohertz range, with the cap in, we're probably getting a gain of around about 6, but without the cap we had a gain of nearer to 40. So that cap really does reduce the gain, but it also really cleans up the signal and takes off any frequencies sort of higher than 3 kilohertz quite significantly. So all of that was really just with the first transistor involved. So now what we're going to do is we're going to bring back the second one, which is here, and I'm going to put that back into the circuit. And I'm also going to put back in this coupling capacitor that joins stage 1 to stage 2. and we're going to move our oscilloscope probe so that it's going to pick up off the output of stage 2. Right, and we still have like a 70 millivolt signal going in at the input point from the signal generator. But now at the output of stage 2, we're already at nearly 3 volt, or basically 3 volts peak to peak. And I haven't got the stage 3 transistor in, and I'm just also going to remove the coupling capacitor to stage 3 just in case it had any impact at all, which I'm not really expecting it will. Yeah, so we still have our 3 volts peak to peak now coming out of stage 2. Now the design of the stage 2 is almost identical. In fact, I think it is identical. So it's got that cap with the feedback again. It's still a 470k feeding from the collector to the base with the same collector resistor value. If I was to remove that 2N2 cap there, I'd expect the gain would go up, but my frequency sensitivity would disappear. So let's experiment with that. So the cap is currently in. We've got the and I'm just going to now move up from 1 kilohertz up to 30, and we'll watch the blue on the scope. And now we're at 30 kilohertz, and you can see the gain massively dropped off, which is what we'd expect based on what happened with stage 1 as well. And I'm going to go back to 1000 kilohertz, and now I'll take out that cap, and we can see we're hitting rail to rail again. So the gain is so much that we can't even cover the whole of the range after the gain because of the it's too much. And if I start pushing the frequency up to 30 kilohertz, well, the gain really hasn't dropped off that much, or at least not enough, because we're hitting rail to rail anyway. It's not enough to even bring it out of that state. So I'll just double check that, but I don't think that's the case. Yeah, so you can still see it flatlining on the bottom here, so it's still hitting the limits of the range based on the supply voltage. So that's what the second cap is doing. And I guess if I put that cap back in, now that we are getting nearly 3 volts peak to peak, by the time we've done our second stage, our gain is almost the same as we were getting with the first stage only with no cap in it, but we're getting pretty significant gain again. Just going to draw our circuit now as it is. So we've got out of stage 1 the 22 nanofarad cap going in to the base of stage 2 transistor, which goes straight to ground from its emitter. From the collector side, it also has a 4.7k resistor and a 470k resistor going from the collector to the base, and it has the 2.2 nanofarad cap as well. And we were doing all our measurements from this output from stage 2 effectively. That's what we were doing. Okay, so let's now start talking about stage 3. Now, the stage 3 scenario doesn't have that feedback capacitor in it, and I assume that's because they feel like they've already taken off enough high frequency noise already by that point. It does have this mystery cap here in one version of the picture with the Q4 in it. We don't really know for sure what that does yet. There is a difference in the resistors. This is 1 meg and 10k instead, but I'm just going to start putting it back in. So I'm going to put in this this coupling cap to join in the circuit. make sure I've got that. I'm going to take my output measurement from what's going to be the collector of the final transistor, and we'll find our final transistor and we'll slot that one in as well. Okay, and what we've got going on here is that we are going rail to rail hard with the 70 millivolts peak to peak that we're providing it. So this looks like it can easily give enough a voltage change for a microcontroller to pick up based on an input of a 70 millivolts peak to peak. And I'm really curious about what this 22 nanofarad capacitor is for here. So let's put that in. It runs, according to the diagram, it's running between the collector and ground. So I've got a little grounding wire here, and I'm going to put that in. Okay, so what that's done is changed the shape of the waveform that we're getting out, so that we've got this curve rising up. So I think what's going on here is when this transistor is on, then anything at the collector is just getting shorted straight through the transistor to ground. So that's what we're seeing here with this very vertical drop-off line. But when the transistor is off, then the voltage from the power line is coming in through this 10K resistor and slowly charging this cap. And that's why we're getting this nice curve going on here. And I think it looked a little bit, if I just take that away again, I'm going to pull the cap out. Get my... So I guess what that would mean would be if you would, and see how we've got this sort of noisiness going on in between each point here. This could really interfere with the number of pulses that the microcontroller would be counting in a fixed period of time to work out whether it's got like a forward, drive forward or back signal. So I think this cap is actually important and meant to be there, because once you put that in there, we really have a nice, only one rise through the range from 0 to 5 volts there with it in, so it's not going to confuse the microcontroller. It'd easily be able to count 1, 2, 3 pulses like that. So that, I think that cap is there for that reason. Now let's experiment with what happens if we vary up the frequency. So I'm going to boost that a bit, and you can see, yeah, very quickly the blue voltage range has dropped off. Now it's only 3.3, and I've only gone up to 5,000 kilohertz, so that filtering that was going on in stages 1 and 2 is definitely doing that. I'll bring it back to the around 1,000. So now let's experiment with how low of a signal we can actually get in. So we currently have 70 peak to peak on the input signal, so I'm going to switch to amplitude mode here and then start dropping things off. Okay, so now my input signal is 55 maybe peak to peak, and still the blue line is the full 5 volts. Back it off a bit further. So now I have an input of 30 millivolts peak to peak, and still, yeah, it's pretty clear. We're still getting our pulses that are going rail to rail 5 volts, so it'd be able to be picked up by the micro. I'm going to drop it a bit further. Alright, so probably around about 30 millivolts peak to peak. It kind of gets messy and is doing less than 5 volts now. And interestingly, the signal generator thinks it's only putting out 5 millivolts, so that's probably meant to double it. But yeah, so we have a large amount of gain, and we're not going to need a very big signal at all from the front end of this to get enough out here that this microcontroller can measure stuff. Alright, I think that is enough for one video. We've talked through the entire sort of gain stage of this. Hopefully in another video I'll be able to get the front end receiver part going, and we might do a video too around about, maybe we'll use an Arduino or something to perhaps count these pulses based on what we're getting out of the signal generator, but when we're only putting out such a small signal out of the signal generator that we wouldn't normally be able to measure with an Arduino. Okay, thank you very much for watching. I hope that was interesting. Bye.